In our reference table, there's a map dedicated to plate tectonics. This map shows most of the plate boundaries across the Earth's surface and the major and minor lithospheric plates. Along the bottom, there's a key telling you the motions associated with each boundary type. The way that you use the key along the bottom is very simple. A question could be, what's the relationship between the Nazca plate and the Pacific plate? So you would find the Nazca plate, here it is, and the Pacific plate, here it is. And what's the relationship between the two? Right in the middle, there are two arrows separating. That relates to a divergent boundary. Unfortunately, this does not hold all the information you need to know about plate boundaries. And that's really what this video is for. So let's get started. We'll start with transform boundaries. Typical transform boundary involves this type of motion. Two lithospheric plates pushing past one another. This process generates a great deal of seismic activity. Earthquakes are very common at transform plate boundaries. Where these two plates meet is often exposed or visible, and that's called a fault. In the United States, an example of a fault would be the San Andreas Fault, located on the west coast of the United States in California. At this plate boundary, the North American plate is moving northwards, or I should say northwest, relative to the Pacific Ocean plate, which is kind of moving southwards. Let's talk about the convergent boundary. So convergent boundaries actually have three types. Let's get started. So our first example is an oceanic continental convergent boundary. That's where the crust of the ocean is being pushed towards a land mass. As this occurs, the basaltic composition of the oceanic crust is more dense than the continental crust. So the continental crust overrides the oceanic crust. As one plate is pushed beneath the other, the process of subduction occurs. Subduction is when a lithospheric plate is pushed into the mantle underneath another lithospheric plate, usually due to a higher density composition. The result is that lithospheric plate is melted. Also, a feature at convergent boundaries are ocean trenches, large, deep openings that are the result of one tectonic plate being pushed beneath the other. Also a feature at convergent boundaries on the continental side are volcanoes. As the subduction process occurs, that lithospheric plate gets melted and plumes of magma rise, eventually break through, channeling magma up to the surface. And finally, earthquakes are also common at subduction zones. Those earthquakes can be shallow earthquakes right at the surface, or deep, deep earthquakes when the subduction process is taking place. This is an example of a convergent boundary between the South American plate and the Pacific Ocean. As these two plates move towards each other, the Pacific Ocean plate is more dense and it sinks beneath the South American plate. The Andes Mountains were created because of this subduction process, but also shown in the diagram is the Peru-Chile Trench, which is a deep ocean trench formed from this convergence. So another example of a convergent plate boundary is between two oceanic plates. Very similar to the oceanic continental example that we just looked at, one plate is being subducted beneath the other. Only this time, there's a new feature being created, and you can see it there in the diagram. It's called a volcanic island arc. So picture the ocean where it's just water, but one lithospheric plate sinks beneath the other, and over time, from subduction, creates a chain of volcanic islands. Trenches are also a feature here, just like at the oceanic continental convergent boundary. And we have one more example, and that is a continental convergent plate boundary. At a continental plate boundary, we have mountain building. Because both types of crust here are the same density, instead of one subducting beneath the other, they push upward to build peaks. So the best example would be the tallest peaks on Earth, which are located here between India and Asia. These are the Himalaya Mountains, where Mount Everest is located, the tallest peak on Earth, so to speak. And it was created from the Indian subcontinent converging with Asia, and as the process continues, it grows the mountain chains upwards because the crust is being pushed up. And finally, our last plate boundary, the divergent plate boundary, where plates move away from one another. At divergent plate boundaries, we also have examples where you can have oceanic and oceanic crust, or continental and continental crust, but either way, they're both really the same because the two pieces of the Earth's crust are being pulled apart. So here's an example of what a divergent plate boundary looks like. The Earth's crust is being pulled apart and it gets wider because new material is being added in the center. That magma is being channeled up. It, in this case, enters into the ocean water and it builds up the crust over time. It's adding new layers of rock. So when this occurs in the ocean, we wind up with a feature called a mid-ocean ridge. And a mid-ocean ridge is an area where new rock is being created, and in the process, it's pushing the other sides or the other lithospheric plates away. Here's the Atlantic Ocean, and the Atlantic Ocean has a scar running down the center. This is called the mid-ocean ridge, and this represents an area where new ocean crust is being created, pushing the North American plate west and pushing the African plate east. And as this occurs, it makes the Atlantic Ocean get wider by pushing the two continents further and further apart. We call this seafloor spreading. We have two pieces of evidence that support the idea that the seafloor is actually getting wider. One, if we were to measure the age of the rock at that mid-Atlantic ridge, we would find that it's younger than the rock further east or west of it. So new rock is being created at that ridge system. We could also look at the polarity of the rocks in the crust. Because of the Earth's iron content in the Earth's liquid core, some of that gets into the rocks. And because of the north and south pole of the Earth, it gets polarized. So deep in the Earth, we have an iron core. Some of that iron gets into the rocks, and because of the Earth's magnetic field, it gets polarized in a certain direction. Every 300,000 years, there's a reversal in the polarity of the Earth's magnetic field. And when we look at the oceanic crust, that's something we can detect. We can actually see that there are alternating bands of polarity, which are representative of the shifting poles. And that's our evidence that the seafloor is getting wider. The other example of a divergent boundary is between two continental crust plates. It starts with a rift valley, which eventually separates and widens, filling with water to make a full ridge system. So the example that we were just looking at, where we were in the ocean, the mid-Atlantic Ocean ridge, that came from two pieces of the Earth's continental crust pushing away from each other and eventually becoming the Atlantic Ocean. So as an example of that, the North American plate and the Eurasian plate used to be together. But over time, because this was a divergent boundary, they separated and created a rift zone. An active rift zone exists in the Red Sea. The two plates here for East Africa and Saudi Arabia are actually being pulled apart and making the Red Sea get wider over time. Eventually, the Red Sea will open up and probably become a new part of either the Indian Ocean or the Atlantic Ocean because of its location. There's one more thing that I want to discuss that is related to plate boundaries and plate tectonics. And it's that the areas that are sometimes the most geologically active in terms of volcanic eruptions, like Hawaii and Iceland and the Galapagos Islands, and even Yellowstone National Park, are not necessarily associated with plate boundaries. If I looked at those examples, except for Iceland, they're pretty far away from an actual plate boundary. They're not sitting at the location where two plates meet. They're actually sitting in a region called a hotspot. And what geologists refer to as a hotspot, when there's a break in the Earth's crust and the mantle is exposed, and as a plate rides over that space, new rock is created, opposite to the direction that the plate is moving. So when you think about Hawaii, which is a series of small islands, each one was created by the Pacific Plate passing over a hotspot, creating new rock in a chain of islands. So that's it for plate boundaries. There's a lot of information, so please review this video and make sure that you are comfortable with each example. So that's it for now. Thanks for watching.